Periodical cicadas have got to be some of the biggest gatekeepers in natural history, and if you give me a couple minutes, I can explain why. So, cicadas in the genus Magicicada in North America spend most of their lives living underground as immature nymphs before emerging, depending on their brood, after either 13 or 17 years to reproduce as adults. And I'm sure you noticed that both 13 and 17 are prime numbers. This is actually one of my favorite cases of math kind of randomly popping up in real life, because it's one of the few good examples I can think of where it's discrete number theory stuff going on. So where are these prime numbers coming from? Why have cicadas adopted prime number based life cycles? The first really compelling explanation we got for this was the predator satiation hypothesis. The idea being that if all the cicadas emerge at once, the predators can't possibly eat all of them, so there's almost a safety in numbers. However, the predator populations, whether it's mammals, reptiles, or birds, can't ever increase their population to match the cicadas because they get starved out in all the years while the cicadas are underground. That explains having a long reproductive cycle, but why prime numbers specifically? The effect of prime numbers is it stops any predator or parasite with a life cycle that's some factor of the duration of the cicadan life cycle from matching up with the cicadas every a certain number of cycles. For example, let's say the cicadas had a 15-year life cycle. A predator or parasite with a 5-year life cycle on every third cycle would match up with the cicadas again. But if the cicadas have a prime number life cycle duration, predators can only match up consistently with it if their life cycle is at least as long, because there's no smaller factors of a prime number that they can increment their life cycle at. Stephen Jay Gould used the periodical cicadas as a secondary example in an essay he wrote primarily about bamboo on predator saturation. But in that essay in the 70s, he was careful to point out that the theory remained unproven. And in the intervening time, a lot of complaints or problems have been brought up with the predator satiation hypothesis specifically for explaining the life cycle of the cicadas that are pretty hard for the theory to contend with in this context. One of the big questions that gets asked of the predator satiation hypothesis in the context of cicadas is how the extended life cycles got started. It works really well when everyone's on the same cycle and it's a prime number, but if you start with a population that's reproducing every year or on a smaller number of years as its cycle, there's not really any individual advantage to any cicada that starts to adopt a longer lifestyle. Also, if it's such a great strategy, we should see it adopted more often, which we don't. So both of these complaints, if you will, have a lot to do with the initiation of the strategy. In the former case, where we're asking, just give me a plausible set of steps to get to it. In the latter case, saying, well, if there is a plausible set of steps, why don't we see it happening all the time in all cicada populations? Because there's lots of cicada populations that don't adopt these synchronized long reproductive cycles. And so there's an alternative theory that has come into favor in the interim that does a bit of a better job of addressing these concerns, while also being compelling, standing alone in its own right. And we're going to call this the hybridization hypothesis. And what I like about it is it gives us a step-by-step series of events from some cicadas without any kind of special life cycle up to the 13 and 17 year cycles, well synchronized, that we see in eastern North America today. So the first event we have here is the presupposition that all this was set off by a period of relative coolness in the geological time period during the Pleistocene, thereabouts a couple or a few million years ago. This is not good for the cicadas because they depend on having appropriate temperatures to reproduce and live properly. If they emerge from the ground in a year when the temperature is not so good for them, they could just straight up die out. This cold weather could have either, depending on how you want to present the hypothesis, directly caused the larvae or the nymphs of the cicadas to take longer to mature underground, explaining the length of the reproductive cycle getting started, or it could have selected for longer reproductive cycles. In that case, the explanation being that if let's say there's periods of like 1,000 or a couple thousand years of cold, the more times that you complete your reproductive cycle while it's cold, the bigger your risk that you're going to have a bad year where it's too cold and you die. and so it's an adaptive strategy to just spend longer underground, take fewer chances. Additionally, the challenging environment posed by the cold would have also just reduced populations, which would have favored synchronization in when each brood of cicadas emerges from the ground. Because if you emerge from the ground and there's no one around, you don't get to mate, so you want to make sure you're in line with all your peers, if you will. So now we've got an explanation for this protracted life cycle, and maybe we can start to explain why it's synchronized. But why do we see these prime numbers pop up? And this is where the hybridization part of the hybridization hypothesis comes into play. The idea here is that the cicadas who had the good genes with the long reproductive cycles, or the exact number of years that could let them sync up nicely, were in a good position, and they did not want to share their genes with anyone else. Or they only wanted to be reproducing with the cicadas that also share these, because if you hybridize with another cicada, you could lose your protracted development that gives you less risk of the cold, or you could get some intermediate number of years between the two mates that throws the offspring out of sync with all the other cicadas, so then they come out of the ground and they can't find mates, so they have to gatekeep their genes. And so the best way to do this, or the way that minimizes the overlap between different broods, is to have reproductive cycles based on prime numbers of years. The reason for this would be that if you have two prime numbers, the lowest common multiple of them is their product. And so that basically makes it take as long as possible between periods where two broods with a different number of years of maturation will overlap with each other. And again, they want to minimize the overlap, minimize hybridization. If a brood has a composite number, well, it could have a lower common multiple, so it could overlap more often than simply the product of the two durations of the cycles, which isn't good because now we have more hybridization, more potential loss of genes, or more potential loss of synchronicity with the other offspring from the brood. And that's not good. That gets you killed when it's cold like this. And also, once we do have that protracted life cycle, we also could start to see a bit again of what is properly called the Alley effect, which is where the fitness of individuals is positively correlated with population size, which isn't usually the case in biology. Because when you have a ton of animals around, they usually compete with resources. But here, with the cicadas, especially when the population is low, you need other individuals around to reproduce. And when you have a ton of cicadas, well, it helps you to have other cicadas around to saturate the predators. And so I wouldn't rule out, even if you are a fan of the hybridization hypothesis, I wouldn't rule out the predator satiation hypothesis. I think the one better informs the other, because we could have the scenario I just presented with the hybridization hypothesis give us this odd prime number life cycle situation, but a kind of byproduct of it that could help it remain stable is predator satiation, where now all the cicadas come out together at these weird times and the predators can't sync up with them. Originally the cicadas were doing this to avoid syncing up with each other, but that had the byproduct of making it hard for predators to sync up with them. And so now that's kind of, I hesitate to call it an exaptation, but I can't think of any reason why not. But it really supports maintaining these life cycles in the cicadas, even though we now no longer have these cold conditions that kind of force them to be a thing in the first place. And of course the other thing enforcing them is again the Alley effect, where any cicada that's off of a cycle just has no one to mate with. However, everyone seems to say that the hybridization hypothesis needs the genetic basis of the timing of these cycles to be properly validated, and as far as I could tell, no one's done that yet. And I still see lots of popular publications put forth the predator satiation hypothesis as the primary reason why we see these cycles. So first of all, the theories are not mutually exclusive, and both theories seem to get lots of play, at least in the popular media. In summary, our best explanation for why we see prime numbers pop up in the reproductive timing of cicadas is a result of a time of intense stress in past geological time, where it was favorable to isolate or gatekeep good genes for the conditions from other individuals in the population. This gives us a pretty compelling explanation for how it came to be, and the reason why it continues to be the case is a result of Alley effects between predator satiation and reproductive isolation. I think this is a really good example of how scientific theories build on each other, because the predator satiation hypothesis kind of covers one part of the Alley effect and is the thing maintaining cicadas in this state right now, or at least a part of it. But this story was further bolstered by the addition of the hybridization hypothesis and bringing the cold climate into it to explain how we got to the point we see today. 2024 is actually going to be a big year for the periodical cicadas, because for the first time in quite a while, a 13-year and a 17-year brood that are right beside each other in the United States are going to come out at the same time. You should be able to figure out how often that happens actually, but I'll cut to the chase, and it's every 221 years, because 13 times 17, and we know the lowest common multiple of the two life cycles is just the product of them, because they're both prime numbers. Yeah, thanks for watching.